Assalamu alaikum. Can you hear my voice? Okay. Uh, Unfortunately, we couldn't join to the class on Sunday. So uh, we should prepare and should schedule some new times new, for some classes that we lost them during the term. I will announce the program for those classes in the WhatsApp group. You can join to the class, or you can uh, watch the recorded contents after the class. Okay. Is there any question from the last week, from the last lecture? Is there any question? Okay. Uh, During the last lecture, we talked about rule-based classification, and we said that we can use if then else or if then rules to find the class of records. However, sometimes it maybe we have some conflicts uh, on the results, and maybe in one or more than one rules became fired according to their antecedents. Okay, so we say that we need to resolve these conflicts using decision list or size ordering or class-based ordering or something like that. However, one of the best and easiest way to uh, create a rule-based classifier is that using a decision tree. When we create a decision tree, uh, simply we can extract rules from the tree. You can find them on the element in the LMS. All past recorded contents are available on the in the LMS. Please go to the homepage of the course. In the recorded contents of the classes section in the homepage of the course, you can find the recorded content. Then you can watch them after the class. Okay. For example, here we can say that if age is between 31 to 14, so the class label is yes, or by computers is yes. Okay, it's a rule. It's a simple rule. For example, if age is less than 13 and the student is yes, then the class label is yes. Today, no. Today we have not exam. I changed the date according to the request, I change the date to Friday. Okay. Uh, mm, the rules, I can use other methods too. Others, other methods too. For example, we can use sequential covering methods instead of using a decision tree. We can use sequential covering algorithms to extract the rules directly from the training data. For example, FOIL, AQ, CN2, RIPER are some of those algorithms. We say that these methods are sequential. Why? Because they are learned sequentially. For example, for a given class CI, they will learn all tuples that belongs to the class CI and not belongs uh, to other classes. Okay, so at each time they just learn about they just learn the learn rules about a single class. After completing the learning rules about a predefined class, we can remove all the tuples uh, belongs to that class. For example, I'm looking for the rules for class 3, C3, okay? After finishing the learning process, I can remove them. I can remove them uh, from the list, from my list, okay? I'm removing all the tuples belonging to class C3 after the learning and learn, for example, about class 4. Just it's a repeating process until until termination conditions. For example, uh, we repeat the process until all examples in the training set would be removed from the list. When the training list became empty. Okay, when the training list became empty, I can terminate the learning process, for example. Or I can terminate the process when the quality of the rules reach to a user specified threshold. Okay. So here, if I compare this method with the decision tree method, in decision tree, we can learn all the rules simultaneously. But here, I'm learning sequentially, one by one. After finishing one rule, I can start another rule for a new class. Okay, so I can use this pseudocode. For example, while there are enough target tuples in my space, I can generate a new rule and remove the positive target tuples under that rule. Okay. Here, for example, firstly, I'm generating a very general rule. Then I can add more condition, more, and more until reaching to a very specific zone. For example, here, the third rule is A3 is equal to 1 and A1 is equal to 2 and A8 is equal to 5, for example. Here we can see that the first rule covers some areas in positive examples and in negative examples. The second rule still covers some parts from negative examples, but the third rule is completely placed in the positive example area, in the red area. Okay, so we will continue to create new rules to reach a predefined quality, predefined accuracy in the rules. If I choose the first rule, I can see that some examples, in this rule, the first rule, covers some positive examples and it covers some negative examples. Also, in the second rule, we have a similar behavior, but in the third rule, we can see that the third rule only covers the tuples in the positive area. It does not cover negative examples. Okay? We call this method as learn one rule. Okay, so the strategy in learn one rule is that firstly we start from a most general rule with no conditions, and one by one we are adding new attributes to the rule using a greedy depth first strategy. We are choosing the attribute with the most improves in the rule quality. Okay, we are choosing the rules and choosing the attributes and adding them to the rules one by one. And after adding each attribute, I should use a rule quality measure. This measure shows me the current rule shows me the status of the current rule, the accuracy of the current rule, or the coverage zone of the current rule. For example, in foil and Ripper techniques, we will use foil gain measure as a rule quality measure. We can use a foil gain measure. You can see the foil gain measure here. This matrix is an extended version of information gain measure. Look at this. It's similar to information gain. We talked about information gain in the past. Okay, foil gain uses a similar structure. Using this measure, we can choose some rules with high accuracy and with a very good coverage. But I'm trying to cover more rules, more tuples. However, if my test tuples are independent, to prune a rule, we can use a measure full prune. What is this? Full prune of rule R is equal to positive minus negative divided by positive plus negatives. These positive and negative signs are related to number of positive or number of negative tuples covered by the rule R. So using the foil prune measure, we can find a position for pruning the data. For example, if a foil prune for a rule is higher than the foil prune for the last rule, we can prune the rule R. Okay, so we are looking for higher values for foil prune before applying the pruning method. Okay. Until now, we talked about decision trees, Bayesian classification, and rule-based classification. We have lots of too many numbers of classifiers. You can find them in different sets or different applications. Okay, but the next question is that how I can evaluate my model, how I can choose or select a model, because there are several classification techniques, but which of them is better than the rest? It's a question. It's an important question. How I can measure the accuracy of one classifier? Is there another measure or metric for something like that? Okay, because when we are talking about creating a classifier, creating a model, we are using train set records. But when we are looking to test the classifier, we have to use the test set of tuples. We need to test all classifiers capabilities against new tuples, against unseen tuples. Okay, so we need some measures, some methods to calculate this accuracy or something like that. Here, firstly, we should talk about some related methods of algorithms related to the accuracy, to measuring the accuracy. For example, we should talk about holdout method, random subsampling, cross-validation, bootstrapping, and something like that. And also, when we are talking about classifiers, we should talk about confidence intervals of the results. Or we should make a cost-benefit analysis and ROC curves to show that if if a proposed method is good, yes or no. If a proposed method is cost effective, we need to define some measures to answer these questions. Okay, we have a specific matrix, or its name is confusion matrix. In this matrix, we have two rows and two columns. For example, belonging to class C1 and not belonging to class C1. Okay, here in the middle of this table, you can see some specified measures. For example, true positive, false positive, true negative, and true positive. False negative. True positive means that the actual class label of a tuple is C1, and I'm predicting that the class label is C1 too. So I'm truly predict the class label positive for a tuple with class label, with positive class labels. False positive means that actually my class label is not C1, Okay. In false negative, I'm predicting the class label is not C1, but in reality, it's not. Okay. And in true negative, the actual class is not in true negative, we can see that. So here we have four different okay. In this confusion matrix, we have such records: true positive, true negative, false positive, and false negative. Here we can see that in true positive and in true negative cases, the actual class of tuples is equal to the predicted class label. But in false positive and false negative cases, the predicted value is not true. They are wrong. For example, in false positive, the actual class was not C1, but the predicted class label was C1. Or in false negative, the actual class was C1, but our model predicts not C1. Okay, how I can use this confusion matrix for my calculations? Look at this, for example, in our last example, buying computer, we gather information from 10,000 customer, and I'm seeing that 6,954 users has class buying computer, and also they buy computer. 46 of them has class buying computer, but our prediction is not true. Our prediction is that those tuples are belongs to no buying computers, and so on. Also here we can see in the last rows or in the last columns of the table, you can see total amount of data in that record, in that table. For example, totally in our dataset, totally we have 4,000, 7,000 clusters with classes and 3,000 tuples with the class no. Also, we predict in 7366 cases, we predict We predict that the class label is yes, or we predict that the class label is no. Okay. So simply we can use confusion matrix to here you can see that in the columns and rows, total number of samples in those cases are written in here. 7366 cases are predicted as class by, and 2634 cases are predicted as non-buying computers. Here we can see that in this case that simply you need to add or subtract the values to find other methods. According to this table, to the confusion matrix, we can define some measures for ourselves. For example, we can talk about accuracy of the classifier in this way: true positive plus true negative divided by all. Look at this, all is here. Total number of records in this dataset. Here we define that accuracy is the total number of records that we predict their class labels with 100% precision. Okay. So here you can see that in this confusion matrix. Don't worry, Muhammad. I will give them to you and the rest of the class. Don't worry about them. Just do your assignment, your current assignment. Labels. So in accuracy, you can see that accuracy is number of records that we predict them truly or correctly. So true positive plus true negative divided by all, by total number of records. Maybe yes, Hannah. Here, for example, the true positive is 69 40 54, and true negative is 2588 divided by 10,000. Okay, so you can find the value of accuracy. It's value between 0 to 1. The accuracy is a value between 0 to 1. And also you can say that the error rate is 1 minus to the accuracy value. What about our error rate? Error rate means that we predict the labels wrongly, or prediction was not correct. So here, false positive and false negative cases. In both of these cases, our prediction is not true. So for error rate, we say that false positive plus false negative, total number of records in false positive and false negative situation are wrong. We divide this number of cases into total number of records. Okay. So simply we can use this measures, accuracy measure, to define the quality of my classifiers. But there is one important note here. All data sets may be balanced or may be imbalanced. What does it mean? When we are talking about a balanced data set, it means that total number of records belongs to each class, total number of tuples or records belongs to each class is similar to the number of tuples in other classes. So we call them a balanced data set. The total number of records in each case is not far from the other cases. But in most of cases, all data sets are in balance. For example, if I create a data set about the conditions of COVID-19 among some people, I'm asking different people, have you COVID-19 or something like that, or I test them, okay? I know that maybe 1 or 2% of people in the society have COVID-19, okay? Or I can see similar conditions for example, cancers, or for example, HIV illness. In all of these cases, you can see that there is a minority and there is a majority class in dataset. The majority class has most of the records. In the dataset, and total number of records belongs to the minority class is a few, just a few number of records belongs to the minority class. For example, just 1% of people may have cancer, for example, lung cancer. I don't know, but I know that their total number is very low. Okay. The problem with imbalanced data set is that the majority class strongly affects the accuracy. For example, if I know that just 1% of people in a society has, for example, HIV virus or has cancer, okay, 99% of people in the society have not cancer. Just 1% has cancer. Okay, so simply if I say, okay, all of you are healthy, none of you has cancer. With 99%, my statement is true. With 99%, my statement is true. But I know that, for example, in cancer illness or in HIV illness or maybe COVID-19, finding the ill people is very important for me. I don't look for healthy people. I look for ill people, sick people. Because those ill people will put me under financial pressures. I should uh, pay lots of money uh, for those people because of their illness. So in that case, the things that which is important for me is the minority class, not the majority class. But I know that the majority class significantly affects my accuracy, my model, my classification models. So in such cases, we define some more measures. One of them is sensitivity. Sensitivity means that total number of true positive records divided by the positive records. Here, positive records is here, and so you can use this simple method. Total number of true positive here divided by total number of actually true. Because in some cases, although the actual label is true, but I'm predicting it's false. So sensitivity is equals to true positive divided by positive rates. Another measure is specificity, which is true negative divided by negative. These cases here. Okay? This is specificity. True negative divided by n. We have more measures too. For example, one of those measures is precision. Precision is equals to true positive divided by true positive plus false positive. We can say that precision is a percent of tuples that the classifier labels them as positive. Divided by all total actual values. The other measure is recall. Okay. We are defining recall as this: true positive divided by true positive plus in false negative. Recall means that what percent of positive tuples okay. Recall means that what percent of positive tuples did the class label as positive. The classifier labels them. In precision, we say that number of true positive tuples divided by total actual positive records. But in recall, we say that percentage of the records who are predicted by the classifier as a positive class. Also, we can combine precision and recall together to create a new measure, for example, F measure or F1 measure or something like that. The F measure is a harmonic mean of precision. And recalls. You can see the equation for F score here. 2 times in precision times in recall divided by precision plus recall. The actual formula is this: 1 plus skewer of beta times in precision times in recall divided by skewer of beta times in precision and recall. If I put beta equal to 1, I can reach to this equation. We call it F1. So we can change beta in this case. For example, look at this table here. In this case, the accuracy is 96.40%. Okay, the accuracy is 96.40%. But look at this. Only 90 records belongs to class true positive. Only 210 people belongs to class true negative. But look at this, 9,560 cases. Ninety-five 60 records are in the class false negative here, true negative here. Okay. Here we calculate the precision and recall for this confusion matrix. 19 divided by 300 divided by 230 is equal to 39.13. And for recall, we should use true positive or 90 cases divided by total number of real positives. Okay. Here you can see that my accuracy is 96.40%. But its precision and its recall measures this means that these measures shows that the algorithm is affected by the majority class. Okay. So here we define some measures to qualify all classifiers. But there are some other important notes. We should be clear about them. One of them that affects the classifier accuracy very strongly is the way that we split our data set into two separated parts. One of them is test set and the other is train set. Okay, I want to split those parts from each other. How I can do this? So I'm looking for a method to split the data set into two separated parts, training set and test set. The simplest method is holdout method. Holdout method. In holdout method, randomly I'm partitioning the data set into training and test sets randomly. For example, 60% or 65% of records can be in the training set, and the rest of records can be in the test set. Okay. Mostly we use this percentage, 66% of records for training set and 34% are used for test set. But these values are optional. You can change them. For example, I saw in the past, I saw some reports. The others use, for example, 90% and 10% for training and tests. It depends, but most of the time, the others use 66% and 34% for training and tests. Okay, and in this case, we randomly partition the datasets. It means that I don't know which of the records would be in the training set or in the test set. Also, so it's a random sampling method. So if I change my training and test sets, the result will be changed. So if you redo the classification or rerun the classification, you will receive different accuracies, different accuracy values. So the only way to overcome to this problem is that you need to run the random sampling multiple times and gathering the accuracy, for example, accuracy values, and finally report the average values of those accuracy values. Okay. So if you are using a holdout method, you cannot focus on the first results that you obtain from the classifier. You need to reclassify and redoing classification. Okay. The better option, one of the better options is using cross-validation techniques. In cross-validation, firstly, we are dividing data into k different folds or into k different partitions. Those partitions or subsets are mutually exclusive, which it means that they are completely separated from each other. You cannot find a sample in more than one of those folds or those partitions. Most of the times we use k equals to 10 in our calculations. For example, if you use VK, you can see number 10 as a predefined value for k-fold matrix. Okay? So, in cross-validation, I'm partitioning the data into k different mutual exclusive subsets. All of those subsets have equal size. Okay? Then, I'm starting from iteration 1 to k. K different partitions, k different iteration. Starting from 1 to k iteration. In each iteration, I'm using the IS partition. I have k different partitions, okay? K different folds. In iteration I, I'm selecting the IS partition as the test set, and the rest of partitions are selected as the train set. For example, if I have 10 different partitions in the first iteration, I'm selecting the first fold as a test set, and rest of the folds, rest of 9 folds, from folds 2 to folds 10, are selected as train sets. In the second iteration, I'm choosing the second fold as a test set, and the rest of folds would be the training set. In the third round, I'm selecting the third fold or third partition as a test set, and the rest of folds. There are 9 other folds. They are train sets. Okay? In each round or in each iteration, only I'm keeping one of them for test set, and the other partitions are belongs to the partition, to the training set. Here, I'm trying to make a cross-validation technique. Why? Because firstly, I'm creating a classifier model according to 9 different folds. For example, if I use 10 folds, for example, okay, I'm creating a training set consists of 9 different folds, and then I'm testing that classifier with the first fold. Then I'm changing my training set and my test sets, and again I'm creating a new classifiers and with new accuracy or qualification measures. For the third time, I'm creating another classifier with different classification metrics. I'm repeating this for k times, and finally I'm calculating the average values for all k iterations. I'm reporting this value as a final value in this case, in this method if I use the cross validation method. So in this case, I can reach a fair method. I can receive, I have a fair method to compare the results. It's more fair than the holdout method, because in holdout methods, just I'm partitioning the data into two different tests and train sets. Okay, if I choose my training set very clearly, I can receive very good results from the test sets. But in practical cases, I can see that the accuracy of the final classifier would be very low. Why? Because I'm cheating during the creation of testing and training sets, during the partitioning my data sets. I'm cheating at that time. So my results are not fair, are not true. But when I'm choosing cross-validation techniques, during each round, each iteration, I'm selecting another train set, another test set. I'm changing them. And finally, I'm using an average for all of those values. Okay. There is one more method to do this creation. This method is bootstrap method. Bootstrap method works well for small data sets because it uses a replacement method during the choosing the training tuples. It uses a replacement method. Using this method, we can prove that with a uniform distribution, we will select different tuples as training tuples. It means that all of the records in my dataset has equal chance of selection and to put equal chance of selection for putting in the training data set. And after selecting, I can re-add them to the training set. There are different implementation of bootstrap methods, but one of the most common methods is 0.632 bootstrap algorithm. In this algorithm, we define for a dataset with D tuples, we repeat the sampling process D times, and after sampling, replace the selected attribute, selected tuple in the dataset again. It can be proved that about using this step, using this technique, about 62.2% of original data will be put into the train set, and 36.8% of data will be put in the test set. It can be proved mathematically. Why? Because after selecting each tuple, I'm replacing it again into dataset. And again, it has a chance to be selected more than one times. One record can be selected because of the replacement strategy in Bootstrap. One record can be replaced, can be selected multiple times to be a part of training set. Okay? So finally, you can see here 63 and 36. If I look at these values, they are near to the holdout values. I said that in holdout method, mostly we are selecting 66% of records or tuples as training set, and 34% of tuples are recorded as the test set. And now here you can see similar values here, similar measures here. But using Bootstrap is more fair than Holdout, because of its strategy. Selecting training tuples randomly with uniform distribution and with replacement strategy. Bootstrap is better than Holdout strategy. Okay. Okay, that is enough for today. Is there any question? Is there any question? Okay.